Hi everyone, I'm Harish Dixit, representing hardware sustaining from Facebook, and today I'll be talking about optimizing interrupt handling performance for memory failures in large-scale data centers. Facebook has seen a large growth in the past 15 years, with the number of active people climbing to billions across multiple platforms. In all, we see 2.8 billion people using Facebook, WhatsApp, Instagram, or Messenger each month. Before we go into the contents of the presentation, let's take a step back and understand why interrupt handling matters to Facebook infrastructure. With billions of people using the service every day, we have a high bar on the reliability and efficiency of our infrastructure. Our infrastructure is made up of hundreds of thousands of servers, and it needs to cater to billions of application requests every day. These servers are expected to perform at their peak throughputs at all times. We build monitoring systems to measure system events and optimize them. Interrupts are one example of such key system event. Having a large part of infrastructure spend measurable time in interrupts affects services adversely at scale. Hence, optimizing interrupt handling performance provides us with efficiency wins across our server fleet. With that context, let's get started with the contents of the presentation. So today, we will first go over the server architecture, then understand the different classes of intermittent errors, specifically focus on memory error reporting. Within memory error reporting, we'll look into interrupt handling for logging. We will cover two different types of interrupts, system management interrupt, or in short SMI, or corrected machine check interrupts, or in short CMCI. Then we will go into the experiment infrastructure and start documenting the observations. So let's get started with server architecture. A server typically consists of compute units, central processing unit like CPUs, and graphical processing unit or GPUs. And server also consists of memory, which in this case are represented by dual inline memory modules. In addition, a server consists of storage made up of flash or disk drives. The server also consists of network architecture, which is made up of network interface cards, cables. In addition, to connect all these blocks together, we also have interfaces like PCIe or USB. And on top of all of that, to monitor and watch the health of the server, we have a monitoring block called as the baseboard management controller or BMC, and a bunch of sensors and many sensors like thermal, voltage sensors, and hot swap controller are connected to the BMC to ensure that we get the right monitoring metrics for the server. And now that we have understood the different components which make up the server, let's try to understand what are the different intermittent errors that affect these components and how do they impact the system. So let's start with the CPU. A CPU usually encounters machine check exceptions or bit flips. What are machine check exceptions? Machine check exceptions are register level corruptions seen within the CPU under a protected logic. And these machine check exceptions, when caught, result in system reboots. If there are bit flips in the data path in the unprotected logic part of the CPU, these result in data corruptions. Similarly, for memory, if there are bit flips which are seen in memory, but they are single bit flips, then we can correct them by using Hamming codes as part of error correcting mechanisms. And these are classified as correctable errors. And these correctable errors usually show up as interrupt storms and thereby resulting in system stalls. If there are more number of bits which encounter errors in the data from memory, we term them as uncorrectable errors. And these are not possible to be fixed by the Hamming code or the error correcting mechanisms. And these usually follow the same path as followed by machine check exceptions and result in system reboots. In addition, across different components like storage, for example flash or disks, we see that there are other types of ECC errors and as well as RF encoding errors. And in both these cases, these errors result in system level IO retries, which in turn result in system level input-output bandwidth loss. Similarly, for network, we see because of the burst characteristics in the cable or in the network interface cards, we will see CRC errors. And based on the protocol that we use, in some cases we might see packet loss. And in both these scenarios, at a system level, this results in retry of the packet and eventually resulting in network bandwidth loss. And similarly for interfaces, we have correctable errors as defined earlier, as well as uncorrectable errors. And they both result in a similar behavior as seen before. Correctable errors resulting in retries as well as bandwidth loss because of the system stall that they cause. And uncorrectable errors resulting in machine check exceptions received by the CPU, which in turn causes the system reboot. For the sake of this presentation, we will be just focusing on memory correctable errors and look at the different type of interrupt storms and system stall events they cause. Now let's look at memory error reporting a bit more in detail. Memory errors or correctable errors are usually reported by using system management interrupts or corrected machine check interrupts or MCE log. The system management interrupt is implemented by an x86 special mode which is called system management mode, and this is usually implemented as a firmware config. The corrected machine check interrupts are implemented by an x86 kernel driver which is error detection and correction, or in short EDAC, and EDAC implements the CMCI mechanism of handling the correctable error reporting. There is also a third mechanism which is called MCE log, which provides additional features like page offlining, and this is implemented as an OS daemon. In addition to correctable errors, there are uncorrectable errors which can also be reported by system management interrupts or the corrected machine check interrupts. For the sake of this presentation, we will just be focusing on memory correctable errors and the two defined interrupt type mechanisms, one being SMI and the other being CMCI. Let's delve a bit deeper into system management interrupts. So the trigger for system management interrupt is memory correctable errors. On the right hand side, we see a flow diagram for the handling of system management interrupts under memory correctable errors. So when the processor or the system sees that a number of correctable errors have occurred, and if the number is above a certain threshold, this triggers a non-maskable interrupt. And once the non-maskable interrupt recognizes that it is based on memory correctable errors, the control is then transferred to a machine check handler, which then triggers the system management mode. Within the system management mode, the logging implementation of the correctable error is handled, and the message about an occurrence of correctable error is written. And once the message is written, the system exits the system management mode, and then the control is then provided back to the processor to continue normal execution. So graphically, one important thing to note is once the machine is pushed into system management mode, at the same time, all the CPU cores are paused. So all the workloads running on these CPUs is essentially stopped at that point. The correctable error logging is done, and the physical address associated to that particular correctable error, physical address here refers to the physical address on the memory, is once the physical address is captured, then we return from system management mode and then resume the execution of the workload on all the cores. So as a result of system management interrupts, we see that there is a certain duration where all the CPU cores are just waiting for this logging mechanism to be complete. In contrast to system management interrupts, let's look at the corrected machine check interrupts, which we mentioned before with a bit more detail in the slide. So the CMCI trigger is also from memory correctable errors, and the flow for the CMCI architecture is seen by the diagram on the right hand side. So as we can see, from the CMCI flow, we do not go into any system management mode or execute any part of the firmware. The control is directly limited between the processor and the operating system. When a burst of correctable errors is seen, the CMCI handler is invoked, and EDAC then collects the errors from different CMCI architecture registers and repeats the said collection every specified polling interval. So every polling interval, we collect CEs from each of the cores within the processor, and then we aggregate the total number of CEs seen for that polling interval, and one randomly assigned core then logs the aggregated CEs, which is referred to as count per core. So as a result of all of this, we see that the CPU stall occurs only during logging, and the CPU stall is seen only on one core. Before we go further into our experimental observations and results, let's take a step back and look at our infrastructure health monitoring setup and try to understand how that fits into the overall picture. So the experimental infrastructure at Facebook runs failure detection by using a daemon on the machine called as machine checker. So this runs periodically and collects the output. So this machine checker tool does checks for memory, CPU, NIC, and different hardware components. It also reads a lot of system event logs and tries to correlate events and make a smart decision on the health of the machine. So if the machine fails, then an alert is created by using alert manager, which runs off the machine. Once the alert is created, then it is fed into the failure digestion system, which is Facebook auto remediation. So this block picks up hardware failures and also processes different logged information, which is on the machine, on the BMC, and then executes the custom made remediation. This could be reboot, this could be a select cycle, or any scenario of that sort. If this does not fix the machine, then we try to do a low-level software fix with a block called as Cyborg. So this tries to do firmware upgrades or re-imaging of the machine to see if the machine comes back alive because of these fixes. If this does not fix the machine, then we go ahead and create a manual repair ticket. When the repair ticket is created, the DC data center technicians try to carry out hardware and software fixes. In addition, we also log the repair actions for further analysis to understand the effectiveness of repair actions. In addition to understanding the hardware remediation infrastructure, let's also try to understand the production system setup that we used for conducting our experiments. So we have a series of production machines which are all serving traffic to our applications as well as end users. And these are first configured with SMI memory reporting in the first step of the experiment. And in the second step, to get the comparison, are configured with CMCI memory reporting. And then the results are compared. And it is also important to note the remediation policy that we use for saying when the memory is good versus when the memory is bad. So in our current infrastructure, we swap the memory at tens of correctable errors per second. Depending on the memory remediation policy, one might go for different thresholds when going ahead with choosing SMI or CMCI in their infrastructure. In addition to remediation policy, we also use benchmarks. For reproducing memory errors, we try to use stress-app test, which is a Google benchmark available as an open source test utility. And in order to measure performance impact, we use Perl bench within the spec benchmarks, and we augment that with an additional fine-grained stall detector to detect CPU stalls. With that description of production system setup, let's start looking at different observations that we have been able to make through these experiments for memory error reporting. One additional thing before we go for the observation is to note that memory errors in a production environment are random occurrences and therefore have no fixed periodicity. This fixed periodicity is usually seen in an experimental error injection setup. But in this graph below, when we plot time along the x-axis and the correctable error rate across different machine types on the y-axis, we see that the error rates are not predictable. You can see that three different machines or three different machine types have different error rates at different intervals of time. And as a result, this is a production traffic experiment and not necessarily a synthetic experiment done by using error injection. With that, let's get started with the observations that we have been able to make through the sets of experiments. Let's consider an example caching service application for making the first observation. On the graph on the right hand side, we see that the time is in minutes on the x-axis. On the left y-axis, we see a request efficiency percentage. On the right hand y-axis, we see a correctable error count scale for the number of correctable errors seen on that machine. Request efficiency refers to the number of requests that the machine executes successfully within a specified deadline time. If the machine drops the request or is unable to complete the request within the deadline time, we say that as a request drop. So let's walk through the different steps that happens when a machine encounters thousands of correctable errors. So in this case, we see that the correctable errors increase from 6200 to 7300. And the machine under consideration here is configured to use system management interrupt. So because of the default configurations seen in most x86 machines, this results in trigger of SMIs for every n errors. In our example, here the n is equal to 1000. So as a result, and based on our previous understanding that SMIs can cause a stall of all the cores, this increase in the number of errors results in stalls of all the cores of a CPU for hundreds of milliseconds. And as a result of these stalls, the requests which have a deadline-driven mechanism are not able to finish within the specified time because the CPUs are busy spending time in the stall. And thus, we see that the request efficiency drops by approximately 40% when the number of correctable errors increase by a number which trips the threshold for SMI. So, our first observation is system management interrupts cause the machine to stall for hundreds of milliseconds based on the logging handler implementation. This is a measurable performance impact just to report correctable errors for high-speed example caching services. Let's move on to the next observation. So now we saw that system management interrupts have performance impact. How do we detect this performance impact using synthetic benchmarks and not necessarily have this impact our production traffic? So what we initially established was a benchmarking setup using the spec benchmarks, and we ran Perl bench. And through Perl bench, we compared the scores with and without the SMI stalls. So here, we take a set of machines where we run Perl bench and stress app test to try to generate memory errors on a good set of machines. and again Perl bench and stress test on a set of machines where there are a few bad memories. And in both the cases, we saw that the average of scores across multiple runs is the same. So in essence, under SMI stalls, benchmarks return the same scores. In addition, we also wrote a stall detection utility. This stall detection utility detected stalls of hundreds of milliseconds while the benchmarks returned the same scores. And fine-grained stall detection helped us observe CPU stalls. Again, a couple of things to highlight here is we are using stress test to surface memory correctable errors due to bad DIMMs and not necessarily injecting any errors. And the key observation here is benchmark like Perl bench within spec are definitely useful for quantifying system performance, but for variable events and sensitive events, we need to augment the benchmarks with fine-grained detectors to capture performance deviations. Now that we have understood the different characteristics of SMI, let's recap the CMCI architecture a bit before going for comparison results between SMI and CMCI. So the CMCI has a trigger of memory correctable errors, and it only uses the CMCI handler, and EDAC then reads the registers from the CMCI handler based on what is configured as polling interval, and then logs the aggregated CEs, which in turn results in stalls on only one core. Now with that recap, let's go back and try to compare the SMI and CMCI interrupt events. So on the right hand side, we see a graph where on the x-axis we are plotting the number of correctable errors that are seen on machines, and on the y-axis we are plotting the cumulative stall time seen in the CPU because of two different interrupt types. So for the case of SMI, we see that the stall affects all the CPU cores, but the SMI specifically provides the full physical address of the error. In the case of CMCI, we see that the stall affects only one CPU core. And this is evident from the trends that we see that even though it affects all cores, SMI is also a lot more expensive, seen by the growth of this SMI curve versus the single core growth seen on the CMCI curve. So the graph is basically showing us a trend of SMI stall time versus CMCI stall time versus number of errors seen on the machine. And it is also important to note that the results hold for M1, M2 or M3 machine types, since the stalls are a function of error counts. When a particular machine hits this particular error count, this is the number of stalls we would see under the current. So the key observation here is that SMIs are several times more computationally expensive than CMCI for reporting correctable memory errors in a production environment. Now that we have compared the SMI and CMCI results and understood that CMCI provides us with better performance in the production environment, let's try to optimize the CMCI configuration and see if we can squeeze out more performance from different knobs that the EDAC driver provides for accessing the CMCI registers. So here in this graph, we are starting with the configurable parameter, which is the polling interval for the CMCI interrupts, which is implemented through EDAC. So for every polling interval, we log the aggregated CEs on one randomly assigned core, and this causes a CPU stall on one core. In this graph, we are modifying the polling interval to go from 1 second to 40 seconds. And based on the different polling intervals, we are comparing what is the largest individual stall that we will see on one randomly assigned core, and try to understand what is the behavior of the polling interval versus the individual stall time. So as we can see, with increasing polling interval, we see that the amount of time spent in individual aggregate logging by the EDAC driver increases. This is because if instead of polling at 1 second interval, we start polling at 8 seconds interval, for example, the number of messages that are reported by many cores will be more. So as a result, you are aggregating more messages at every particular polling interval, which means you will log more messages, which means you will spend more time logging, and as a result, your individual stall times increase. You can see that after a certain point of time, this value plateaus. The reason it plateaus because all the cores may have seen at least one error, and at that point of time, you are collecting the message from every possible core, and you have reached the maximum number of messages that you can log per polling interval. And that's the reason that after 35 to 40 seconds of the polling interval configuration, in a machine which has M1 error characteristic type, it is possible that you will see a plateauing of the polling interval individual stall time trade-off. In this next graph, we are trying to correlate the polling interval's impact on the total stall time. So just to reiterate, for every polling interval, we log aggregated CEs, which results in CPU stall on one core. Now, if you keep doing this over and over again across multiple iterations of the polling interval, you will see that you will have CPU stall plus CPU stall at the next polling interval plus CPU stall at the next polling interval and so on. And this in turn equals the total stall time that you would see because of logging correctable errors. So here, the trade-off is error visibility frequency versus total CPU stall. And in this graph, we see that the trend reduces. So the total stall time actually decreases as we increase the polling interval. And the reason behind this is the reduced number of context switches that we are doing by moving the polling interval to a higher value. Instead of having a context switch every second, you are now having context switch every 30 seconds. So in essence, if you are logging very few correctable errors every second, where you would cause a CPU stall on one core every second, instead of that, you are now causing one CPU stall every 30th second. So as a result, the total stall time that your CPU spends while giving you the same observability of errors is less. So the key observation here is that we see with an increasing polling interval for EDAC, frequent context switches are reduced. Hence, the total time a machine spends in stalls will be reduced. However, there is also an additional parameter that we would like to monitor when we increase the polling interval. Since EDAC runs by looking at the corrected machine check interrupt registers, those registers have a finite bit width and they can only capture a certain number of errors at a given point of time. If with increasing polling interval, if the errors are at a higher rate, we run the risk of overflowing those counters and causing those counters to start from zero again. And in that case, we start losing the errors per pole. So let's say our remediation policy is based on swapping memory at tens of correctable errors per second. And if we start losing visibility on memory errors, then our remediation policy is going to be inaccurate because of the errors that we have lost by our monitoring. So here, the y-axis is the errors lost per pole, and on the x-axis, we have the polling interval again. And we see that with increased polling interval for EDAC, we run the risk of overflow in error aggregation. And this is to be avoided as this causes us to have issues and bugs in our remediation expectations that are set across our service owners. So in essence, combining the previous observations, we would like to propose the following recommendation. For measuring tens of CEs per second in the production environment, definitely use CMCI instead of using SMIs. And combining the results, we see that at a polling interval of 37 seconds, for our trade-off of error visibility, we see that it is maximized, as in we lose as few errors as possible, while minimizing the total stall time to as lower value as possible. So for our current remediation scheme, we see that this is the optimal point. However, if you have a tighter remediation policy where you want to swap DIMMs at one correctable errors per second, or even lesser than that, say 0.1 correctable error per second, then you would choose a polling interval which is probably higher, but still incurring the penalty of a higher cumulative stall. So the value here is based on the recommendation of the remediation policies. While we understood the different trade-offs involved with the CMCI polling interval as well as the trade-offs with SMI and CMCI, there is a cost associated with CMCI, and that is the ability to do post-package repair. What is post-package repair? Post-package repair is a memory error repair feature which was introduced in DDR4 memories. What this does is it remaps faulty cells with healthy spare cells in memory. So let's say we have an address decoder, and let's say we have a series of cells which are bits in memory, and let's say we have a bad bit. What post-package repair allows us to do is map this bad bit to a spare bad bit within the address decoder. And this remap bit is then used for data input or output. However, to do this, we would require the physical address for performing PPR. SMI provides the physical address of the error. However, CMCI does not provide the physical address. That is one major drawback associated with CMCI. And in addition, within post-package repair, there are two different types of PPR. One is hard PPR, which is preferred because it is persistent across reboots and this mapping is maintained. If this is not maintained, this is defined as soft PPR and this is not persistent. To overcome this drawback of CMCI, we use a hybrid approach where we use CMCI in production flow to minimize performance impact and we use SMI in remediation flow to get the benefits of post-package repair. To understand the hybrid approach, let's walk through the scenarios. Let's say there is a production machine which is configured to run on CMCI interrupt. Now, our periodic health collection daemon now comes in and says sees that the error that is seen on this machine is greater than our predefined threshold for doing PPR. If that is the case, then an alert manager triggers and it says this machine is now a good candidate for post-package repair. And FBAR then implements a remediation mechanism, which is custom remediation, which says change interrupts from CMCI to SMI. Then we would reduce the SMI trigger thresholds so that we trigger SMIs at a faster rate. So in our earlier example, n was equal to 1000, we could reduce n to be equal to 1 or equal to 10. Then we would run benchmarks or memory stress or stress out test. And once the first SMI is triggered, based on the physical address available, one would perform hard PPR. Once the hard PPR is done, the remap is permanent and it is persistent across reboots. We would then change the interrupt type to SMI, from SMI to CMCI, and then return the machine back to production. As a result of this flow, we avoid swapping DIMMs for memories which could have been fixed by using the spare cells and the post-package repair mechanism. So this gives us best of both worlds of CMCI interrupt in production and using SMI in the remediation flow. Now that we have covered the hybrid error reporting approach, let's go to the conclusion and try to summarize the presentation. So we see that SMI versus CMCI. With SMIs, we see hundreds of milliseconds of stalls in production environments, and these can be expensive for a variety of applications. We also see that benchmarks can be augmented to have fine-grained stall detectors so that we can detect CPU stalls. In addition, we saw that CMCIs are more efficient for reporting memory errors in production as they see stalls only on one core and they also see a lower trend. And we also tweaked and went further with CMCI by trying to optimize for different polling intervals and identifying an optimization point for the defined remediation policy. However, there is a cost associated with CMCI that we cannot do PPR, and here is where we use our hybrid implementation to reduce the performance impact in production and obtain the benefits of PPR. With that, I finished the presentation. Please let me know on the Slack community if there are any questions. Thank you.